away from me. No, no, get back. Oh, hi. Hi, students. Hi, this is Dr. Angley, and you might be wondering why I'm in this field full of vicious, hungry dinosaurs, and that's because I'm here to talk to you about fossil fuels. Oh, but wait. I have to come back once. Hi. Okay, I'm actually back now in the primordial swamp. We're actually millions of years before the dinosaurs roamed the earth. And in this area is where we actually started to form fossil fuels. Fossil fuels are formed from decaying plant material and animals, mostly phytoplankton, and they were buried under thousands of feet of soil and was turned into rock and were compressed over time, and we formed things like coal and oil and natural gas. So our lecture today is going to be about the environmental consequences of extracting these fossil fuels and using them to power our modern society, if you will. So take care. I hope you enjoy the lecture, and I'll see you in class in a few days. Hi students, this is Dr. Joe Angley. We are now getting ready to start our study of energy. Because there's a lot of material in this chapter, I've broken it up into 3 lecture videos. This first lecture covers fossil fuels. The second lecture will cover nuclear power and hydropower. The third lecture video will cover what are termed renewable energy sources. This slide presents the learning objectives for this lecture. You should review these objectives on your own. Also note that as you proceed through the lecture, you will be asked to answer various questions. It may take additional research and independent thinking to answer these questions, so please be on the lookout for them. In addition, there are questions to be answered at the end of the lecture. Please bring your answers to all the questions to class and be prepared to discuss them and present some of your results. The former Saudi oil minister, Sheikh Yamani, noted that the Stone Age did not end because we ran out of stones. In the same way, the fossil fuel age will not end because we run out of fossil fuels. In fact, as we will learn in this lecture, we have thousands of years of fossil fuels left to exploit. With so many years of fossil fuels available, why do you think we shouldn't use them? Stop the video now and write down some ideas on why this might happen. Oil, coal, and natural gas are the fossil fuels that we typically think of when we consider energy sources. But fossil fuels also include less conventional sources such as tar sands and oil shales. Fossil fuels are formed from fossilized plant material preserved by burial in sediments and compacted and condensed by geological forces into carbon-rich fuel. Most fossil fuels were laid down during the Carboniferous period some 286 to 360 million years ago. Because these fossil fuels took so long to form, we consider them to be non-renewable resources. The fossil fuels, coal, oil, and natural gas, that have powered the industrial age have brought us many benefits, but have also caused huge social, political, and environmental problems. As we learned in our discussions of climate change, perhaps the most threatening of these problems is that the burning of fossil fuels emits carbon dioxide, CO2, which is changing our global climate. We now get nearly 90% of all commercial energy from fossil fuels. How we'll end our dependence on, some would say addiction to, fossil fuels is one of the most important problems that face us today. In this chapter, we'll look at the costs and consequences of various energy sources, as well as our options for the future. In this lecture, we'll start with the fossil fuels. In later lectures, we will cover nuclear and hydropower, and then turn to renewable sources that could supply all the energy we will need in the not too distant future. To understand the magnitude of energy use, it is helpful to know the units used to measure. Work is the application of force over distance, and we measure work in joules. Energy is the capacity to do work. Power is the rate of energy flow or the rate of work done. For example, 1 watt equals 1 joule per second. If you use a 100-watt light bulb for 10 hours, you have used 1,000 watts, or 1 kilowatt hour. Most American households use about 11,000 kilowatts per year. This table shows the energy consumption of some common household items. Based on this table, what appliance uses the greatest amount of energy in your home? Stop the presentation and go find out how much power your cell phone uses in 1 year. How much money do you think it costs to charge your cell phone for a whole year? Like most industrialized nations, the United States gets a vast majority of its energy from fossil fuels. According to the U.S. Energy Information Agency, oil currently provides 37% of this supply, followed by natural gas, 25%, and coal, 21%. Renewables, hydro, wind, solar, biomass, provide 11%, and nuclear power supplies 9%. In the 20th century, the rich countries of the world, although they made up less than 5% of the total population, consumed more than half the commercial energy. That situation is now changing, however. Rising incomes in China are leading to more energy consumption. China now consumes as much primary energy as all of Europe, and 85% as much as the United States. And because so much of China's energy comes from coal, it has now passed the United States in total carbon dioxide production. The so-called renewable energy resources that make up approximately 11% of our generating capacity, this is expected to change over the next century. Why do you think this may happen? This slide shows the distribution of the world's mineral fuels. Reviewing this map, what parts of the world have the greatest abundance of coal? What parts seem to have the greatest abundance of oil? What continent has the fewest mineral fuel resources? The largest share of the energy used in the United States is consumed by industry. Mining, milling, smelting, and forging of primary metals consume about 1/4 of that industrial energy share. The chemical industry is the second largest industrial user of fossil fuels, but only half of that use is for energy generation. The remainder is raw material for plastics, fertilizers, solvents, lubricants, and hundreds of thousands of organic chemicals in commercial use. Residential and commercial customers use roughly 41% of the primary energy consumed in the United States, mostly for space heating, air conditioning, lighting, and water heating. Transportation requires about 28% of all energy used in the United States each year. Almost all of that comes from petroleum. About 3/4 of all transport energy is used by motor vehicles. World coal deposits are enormous, 10 times greater than conventional oil and gas resources combined. Coal seams can be 100 meters thick and can extend across tens of thousands of square kilometers that were vast swampy forests in prehistoric times. The total resource is estimated to be 10 trillion metric tons. If all this coal could be extracted, and we could find environmentally benign ways to use it, this would amount to several thousand years' supply. But do we really want to use all that coal? Almost all the world's coal is in North America, Europe, and Asia, and just 3 countries, the United States, Russia, and China, account for 2/3 of all proven reserves. Coal is mined in 2 ways, underground mines and surface mines. Surface mining is used for deposits that lie within 100 to 200 feet of the Earth's surface. Coal mining is a dirty, dangerous activity. Underground mines are notorious for cave-ins, explosions, and lung diseases such as black lung suffered by miners. Underground mining involves more human labor than surface mining. Historically, coal was dug by hand by coal miners. Today, underground mines are highly mechanized with machines doing the digging, loading, and hauling in nearly all the mines. Even so, underground mines need more laborers than surface mines. Between 1870 and 1950, more than 30,000 American coal miners died of accidents and injuries in Pennsylvania alone. Thousands have died of respiratory diseases. Black lung disease and inflammation and fibrosis caused by accumulation of coal dust in the lungs or airways is a common disease found in miners worldwide. China currently has the most dangerous mines, with 91,172 killed in mining accidents in 2008. Surface mines, called strip mines, where large machines scrape off overlying sediment to expose coal seams, are cheaper and generally safer for workers than tunneling, but leave huge holes where coal has been removed and vast piles of discarded rock and soil. Strip mining is cheaper and safer than underground mining. However, it makes land unfit for other uses. A common environmental issue associated with coal mining is acid mine drainage. Acid drainage damages streams. Mountaintop removal, practiced in Appalachia, causes streams, farms, and even whole towns to be buried under hundreds of meters of toxic rubble. An especially damaging technique employed in Appalachia is called mountaintop removal. Typically, the whole top of a mountain ridge is scraped off to access buried coal. Mountaintop removal, practiced in Appalachia, causes streams, farms, and even whole towns to be buried under hundreds of meters of toxic rubble. In 2010, the EPA announced it would ban valley fill, in which waste rock is pushed into nearby valleys, but existing operations are grandfathered in. Mine reclamation is now mandated in the United States, but efforts often are only partially successful. Coal burning releases huge amounts of air pollution. Every year, the roughly 1 billion tons of coal burned in the United States, 83% for electric power generation, releases close to 1 trillion metric tons of carbon dioxide. This is about half of the industrial carbon dioxide released by the United States each year. Coal also contains impurities such as mercury, arsenic, chromium, lead, and uranium, which are released into the air during combustion. The coal burned every year in the United States releases 18 million metric tons of sulfur dioxide, SO2, 5 million metric tons of nitrogen oxides, NOx, 4 million metric tons of airborne particulates, 600,000 metric tons of hydrocarbons and carbon dioxide, monoxide, and 40 tons of mercury. This is about 3/4 of the sulfur dioxide and 1/3 of the nitrogen oxide released by the United States each year. Sulfur and nitrogen oxides combine with water in the air to form sulfuric and nitric acids, making coal burning the largest single source of acid rain in many areas. Most people aren't aware of it, but coal burning plants emit radioactivity from uranium and thorium. You'd get more radioactivity living 70 years next to a coal plant than next to a nuclear plant, assuming no accidents at the nuclear plant. It's possible to make either gas or liquid fuels out of coal, but these processes are even dirtier and more expensive than burning the coal directly. Both coal to liquid and coal to gas are environmentally disastrous. In 2010, the United States Energy Information Agency predicted that coal would drop to 44% of America's electrical generation by 2035. Actually, we reached that level in 2011. Currently, the government is projecting that coal will provide only 39% of our electricity by 2035, but that estimate appears to be still far too high. In reality, coal is fading quickly from our energy picture. Only half a dozen new coal-fired power plants are now under construction or in the planning stage. When the last of those plants is finished, about 5 years from now, no other new projects are proposed for the foreseeable future. Federal regulations are part of this decline. The mercury and air toxic standards announced by the Environmental Protection Agency in 2012 will slash the allowable mercury emissions from coal-fired power plants. This was required by the 1970 Clean Air Act, but it was delayed for decades by owners of old power plants who argued that their facilities are about to be closed anyway, and so they shouldn't have to install expensive pollution control equipment. 40 years later, many of those plants are still in operation and still emitting dangerous pollutants. The EPA estimates that new rules will cost utilities about $9 billion, but will save $90 billion in healthcare costs by 2016 by reducing our exposure to mercury, arsenic, chromium, and fine particulates that cause mental retardation, cardiovascular diseases, asthma, and other disorders. In 2012, the EPA also proposed limiting carbon emissions from power plants. If this rule goes into effect, new facilities will be allowed to emit no more than 1,000 pounds, 454 kilograms, of carbon dioxide per megawatt hour of electricity produced. Natural gas plants can easily meet that standard, but it's about half the amount released by the average coal-fired power plant. The only way to meet this limit with coal is to install expensive carbon capture and storage equipment. As of spring 2015, the United States Supreme Court is still hearing cases that may invalidate or modify the EPA carbon emissions. Another problem related to coal is the problem of ash disposal. When coal is burned, it produces ash. In the United States, this amounts to approximately 140 million tons of waste. Coal ash contains a number of highly toxic chemicals, including lead, mercury, arsenic, selenium, and chromium. Most of the material is stored in aging ponds that are largely unregulated by the government. In 2013, a retired Duke Energy coal plant in Eden, North Carolina, leaked 82,000 tons of toxic coal ash into the nearby Dan River. The contaminated fluid traveled through a broken pipe underneath an unlined storage pit, sending 27 million gallons of water from a 27-acre storage pond into the river. Petroleum is formed in a similar way to coal. Organic material, buried in sediment and subjected to high pressure and temperature. An oil pool is usually composed of individual droplets or thin film permeating spaces in porous sandstone, like water in a sponge. We recover about 30 to 40% of oil in a formation before it becomes uneconomical to continue. In the 1940s, Dr. M. King Hubert, a Shell oil geophysicist, predicted that oil production in the United States would peak in the 1970s based on estimates of U.S. reserves at the time. Hubert's predicted peak was correct, and subsequent calculations have estimated a similar peak in global oil production in about 2005 to 2010. Global production has not yet slowed significantly, but many oil experts expect that we will pass this peak in the next few years. About half of the world's original 4 trillion barrels, 600 billion metric tons, of liquid oil are thought to be ultimately recoverable. The rest is too diffuse, too tightly bound in rock formations, or too deep to be extracted. Of the 2 trillion recoverable barrels, roughly 1.26 trillion barrels in a proven reserve, commercially extractable using currently available technology. We have already used more than 0.5 trillion barrels, almost half of proven reserves, and the remainder is expected to last 41 years at current consumption rates of 30.7 billion barrels per year. Middle Eastern countries have more than half of the proven world supplies. Concern about environmental damage from drilling and oil spills like that of the Exxon Valdez in Alaska's Prince William Sound and the Gulf oil spill of 2010 make many observers worry about exploitation in such sensitive areas. Proven oil reserves. 12 countries, 7 of them in the Middle East, account for 89% of all known economically recoverable oil. Numbers add to more than 100% due to rounding. This chart, from the United States Department of Energy, provides an outlook for total U.S. oil production. Notwithstanding the idea that we may have reached peak oil, in recent years we continue to discover and utilize new oil sources. Since the 1970s, U.S. consumers have feared that there won't be enough energy to meet consumer demand. That has changed. We now know that we can recover significant amounts of oil to meet the needs of current and future generations. The U.S. now ranks as the world's top natural gas producer and the second largest oil producer, and may soon pass Saudi Arabia as the top producer. The U.S. Energy Information Administration estimates that U.S. total crude oil production averaged 8.9 million barrels a day in September 2014, driven largely by growth in tight oil production. To put that in perspective, U.S. total crude oil production averaged 7.5 million barrels per day in 2013 and 6.55 million barrels per day in 2012. Recent increases in U.S. oil production due to tight oil are the largest since Colonel Edward Drake drilled the first oil well in Pennsylvania in 1859. We have known for years that shale rock contains oil and natural gas that was too tight or impermeable to allow commercial production. Ongoing research and development optimized two key innovations. The first was hydraulic fracturing, also known as fracking, injecting water under high pressure to create narrow microfissures in the rock. Since the late 1940s, it has been used in more than 1 million wells. Separate research during the 1980s made it possible to drill wells that curve out laterally, thus gaining exposure to more potentially productive rock than was possible with conventional vertical wells. Hydraulic fracturing and horizontal wells were first combined in shale wells in the late 1990s, enabling commercial production of unconventional reservoirs. Most of us hadn't thought much about the dangers of deep ocean oil wells in remote places until the 2010 explosion and sinking of the Deepwater horizon in the Gulf of Mexico. At least 5 million barrels of oil were spilled during the 4 months it took to plug the leak. The well was being drilled in about 1 mile deep water, but that isn't very deep by current standards. For the Gulf of Mexico, the current record is held by the Perdido spar rig, which is drilling in more than 3,000 meters of water, and then to a depth of more than 6 kilometers below the seafloor. Brazil is drilling at a similar depth, about 186 miles offshore. This ultra-deep deposit, which Brazil estimates could hold 50 to 100 billion barrels, could make that country 5th or 6th in the world in oil resources. By some estimates, Venezuela could have more than 300 billion barrels of oil, more than even Saudi Arabia, accessible with current technology, but much of Canada's and Venezuela's new oil resources are from tar sands. Canadian deposits in northern Alberta are estimated to be equivalent to 1.7 trillion barrels of oil, and Venezuela has nearly as much. Together, these deposits are 3 times as large as all conventional liquid oil reserves. Tar sands are composed of sand and shale particles coated with bitumen, a viscous mixture of long-chain hydrocarbons. Shallow tar sands are excavated and mixed with hot water and steam to extract the bitumen. For deeper deposits, superheated steam can be injected to melt the bitumen, which is then pumped to the surface like liquid crude. Once the oil has been retrieved, it still must be cleaned and refined to be useful. The United States also has large supplies of unconventional oil. Oil shales are fine-grained sedimentary rock rich in solid organic material called kerogen. Like tar sands, the kerogen can be heated, liquefied, and pumped out like liquid crude oil. Oil shale beds up to 600 meters thick underlie much of Colorado, Utah, and Wyoming. If these deposits could be extracted at a reasonable price and with acceptable environmental impacts, they might yield the equivalent of several trillion barrels of oil. Mining and extraction of oil shale and tar sands uses vast amounts of water, a scarce resource in the arid western United States, releases much more carbon dioxide than burning an equivalent amount of coal, and creates enormous quantities of waste and wastewater, contaminates rivers and streams, and destroys the boreal forest. However, with rapidly rising crude oil prices in recent years, interest in this resource has rekindled. This is a photo of a Canadian tar sands extraction site. This activity takes place on a huge scale that can be seen from space. Copy and view the link for more information on the environmental issues related to extraction of tar sands. More than half of all the world's proven natural gas reserves are in the Middle East and the former Soviet Union. Both Eastern and Western Europe are highly dependent on imported gas. The total ultimately recoverable natural gas resources are thought to be 10,000 trillion cubic feet, corresponding to about 80% as much energy as the estimated recoverable reserves of crude oil. The proven world reserves of natural gas are 6,200 trillion cubic feet. Because gas consumption rates are only about half of those for oil, current gas proven reserves represent roughly a 60-year supply at present usage rates. Given the awareness among consumers of the impact of greenhouse gases, natural gas companies are emphasizing the advantages of this cleaner burning fuel. This table shows the amount of carbon dioxide produced per kilowatt hour of energy used. As you can see from these data, combustion of natural gas produces about 37% less carbon dioxide than combustion of coal. This graphic presents the proven natural gas reserves by region in 2011. Note that while the Middle East has extensive natural gas resources, their use is limited by problems related to the transportation of the gas to market. To ship natural gas by ship requires it to be cooled and condensed into a liquefied natural gas, or LNG. However, the amount of energy stored in a tanker filled with LNG is equivalent to a medium-sized nuclear bomb, so most major coastal cities do not allow LNG tankers to enter. Specialized ports were constructed for the import of LNG to the United States. Recently, because of the boom in production of natural gas from shale deposits, these LNG ports have been converted to export LNG. Here we see natural gas wells dotting the landscape of the Upper Green River Basin. Drilling for natural gas in tight formations has resulted in an economic boom in many rural cities and towns across the United States. The United States has 3% of world reserves, or about a 10-year supply, but it is estimated that there is twice as much that could ultimately be tapped. These are locations of major natural gas resources in the United States. The Marcellus and Devonian shales, which underlie much of the Appalachian mountain chain, contain a supergiant gas field. Current estimates of the volume of gas in the Marcellus shale range from 168 to 516 trillion cubic feet. Of this total, about 10% is considered recoverable given the current economic climate and available technology. Rising natural gas prices during the turn of the current century, coupled with technological advances, spurred interest in the Marcellus shale in northeastern Pennsylvania. Although the thickness of the Marcellus shale is greater in eastern Pennsylvania, the depth to the shale is also greater. Most of the exploratory and development gas wells in eastern Pennsylvania are drilled to depths ranging from 5,000 to 8,000 feet. Shale deposits are generally tight formations through which gas doesn't flow easily. To boost well output, mining companies rely on hydraulic fracturing, or fracking. Wells are drilled vertically to depth and then turned to be drilled horizontally. Once the well is constructed, explosive charges are set to create perforations, a process called perking. Wells are drilled vertically and then horizontally. Once the well is constructed, explosive charges are set to create perforations, a process called perfing. A mixture of sand, water, and various chemicals is pumped into the well and into the ground and rock formations through the perforations at extremely high pressure. The pressurized fluid cracks sediments and releases the gas. Fracturing rock formations often disrupts aquifers, however, and contaminates water wells. Drilling companies generally refuse to reveal the chemical composition of the fluids used in fracking. They claim it's a proprietary secret, but it's well known that a number of petroleum distillates, such as diesel fuel, benzene, toluene, xylene, polycyclic aromatic hydrocarbons, and glycol ethers, as well as hydrochloric acid or sodium hydroxide, might be used. Many of these chemicals are known to be toxic to humans and wildlife. The U.S. EPA recently forced mining companies to reveal the contents, but not specific fractional composition, of their fracking fluids used on public lands. These are various videos that can provide some pros and cons about fracking. Fracking has created a natural gas revolution and has allowed the United States to become the world's top natural gas producer. However, there is an environmental and social cost. Fracking is associated with air pollution, water pollution, earthquakes, release of greenhouse gases, contamination of drinking water, damage to livestock and crops, and accidents relating to transportation of toxic fracking fluids. New York State has banned fracking. In this lecture, we have learned about energy and how we measure it. We have also learned about fossil fuels and the environmental impact of their use. Fossil fuels remain our dominant energy source, but coal use is declining rapidly owing to problems with the extraction, use, and disposal of ash residues. Oil is an important resource, but easily available oil is not sufficient to provide our needs, and thus exploration and development continues, but in environmentally sensitive areas and by development of shale oil deposits and tar sands at greater cost. A new natural gas renaissance is underway, but with significant effects on residents and the environment near fracking wells. Again, fracking of tight formations provides access to previously unavailable gas and petroleum resources. In this graph, we can see the amount of anthropogenic carbon dioxide emissions from fossil fuels, cement, and flaring over the last 160 years. Because the combustion of fossil fuels leads to the release of greenhouse gases like carbon dioxide, as well as heavy metals and radioactivity, the age of fossil fuels is likely to end sooner than later. Copy and paste the link to view a short movie about fossil fuels and the post-carbon era. Answer these questions and bring them to class for discussion.